Swayam Prabha. Digital India. Educated India.
Okay, so very good morning to all of you. So today in this lecture we'll cover fixed universe successor problem. So this is in the last lecture we have seen how we can do the data structure augmentation to solve for our problem. So we have seen the order statistics problem, dynamic order statistics problem, and we have also discussed the interval tree data structure. So there we have basically used red black tree as our underlying data structure. Then we have done some augmentation on that. I mean that means we have introduced some new field in the node there in order to help us to handle that problems. So that is the data structure augmentation. Now today we'll do the some more augmentation on the data structure, and the today's problem is fixed universe successor problem. So what is a fixed universe successor problem? Suppose we have given some set S, which is obviously dynamic set of n keys. So we have a set S of n keys, and we need to arrange them in such a way, we need to have a data structure for this set S such that we should be able to do this operation in a faster way. Insert, we should be able to insert an element in the set S. We should be able to delete a record from this set S. Okay, we should find the successor. What is the successor? I will discuss. Now here there is a properties on this S, that S is coming from the, we know the set universe where from S is coming. So that is known. So that's why it is called fixed universe. We know the universe. So where from S is coming. So S is a subset of this set universe U. So our keys are coming from this. So keys are basically any values from 0, 1 up to U minus 1. So that is the assumption. That is called fixed universe. So here we have something extra information we have for this set S. Usually we don't know the universe. For so far we have discussed, we don't know the universe. We have some keys, say one, this is one example. Suppose at some point of time we have 9, n is equal to 9, 4. We have 4 element in this set S. This set is dynamic. Any point of time anybody can join. But we know this key values. We know these key values are coming from 0 to 15 because U is 16 over here. So that is the extra information we have. So that is called fixed universe. Okay. So now under this we want to insert an element which is not in S. We want to add that element in S from U because our keys are coming from this set U, the universe. Okay. And also we want to delete an element which is in S. So that is our deletion operation we should be able to do. So these two makes this set S, capital S, dynamic. And moreover, this is a very important query. We should be able to do the successor query. What is a successor query? We should be able to find a successor of an element X, small s, from this universe. I mean, it could be in S also, capital S also. For example, if we want to find the successor of 9, so successor of 9 is 10. I mean the next element, successor means find the next element in S larger than the element X. Okay, so that is what is called successor. Similarly, we can define predecessor, the previous element. So if I ask you what is the successor of 2, although 2 is not there in this set S, but 2 is in the universe. So we can do the successor query for any keys from the universe because keys are coming from the universe. This is the set of all possible keys, you can say, like in this case. So then what is the successor of 2? Successor of 2 is 9. That means the next element in S after 2, what is the next element? Next element is 9. So 9 is our successor of 2. So successor of 2 is 9. So for this example, so successor of 2 is Similarly, successor of 3 is 9, successor of 4 is 9. What is the successor of 1? 1 is in this set. What is the successor of 1? The definition is successor is the next element greater than that element x, which is in the S, capital S. So successor of 1 is also 9. So is this clear, the successor query? So we want to find that element. Given a x from the universe, it could be in S also. Given a x from the universe, we want to find this. We want to find the next element which is in S. That is the successor query. Okay. Now, similarly, predecessor query is the previous element. So both are similar. So we'll discuss the successors. So that's why this problem is called fixed universe successor problem. So we want to find the universe. We want to find an element which is next of after that element which is in S. That is the successor query. Okay. Now, for this dynamic set S, we want to have a data structure. So that is the today's problem. So we want to have a data structure for our. We want to maintain this set in such a way we can do this operation in a faster way. How faster? We'll see that. Okay, so can you suggest some data structure for this? So any data structure you can think. So far we have discussed many data structure in our course. So any data structure you can think for this S. I mean the keys to be stored in there.
Red black BST.
Okay, so BST was suggesting. Okay, before BST we can think for array also. So array of this S. So we can have a array of this for this S. We can have some space over here, and we can array or linked list if you want to make it dynamic like that. So we can put 1 9. So this could be linked list also 1 9 10 50. So just a simple unordered array or linked list. We can arrange this S for this S set. In that case, all the insert will take successor will take the. We have to search in this. So we have to search in this. So it will take linear time. So you set the search tree, binary search tree. So if you arrange this in a binary search tree, these numbers. Yeah. So if we maintain this number in a binary search tree of n elements, so in that case, what is the time of that? If we use the balanced binary search tree, if we don't use the balanced binary search tree, it could be again linear depending on the tree. If it is a if the numbers are sorted or reverse sorted, and if you insert in a binary search tree, it will be like this way or this way, skewed tree. So, but if we make it balanced, if we use the red black tree, our good friend, then we can do the search, or we can do the insert, we can do the delete, we can do the successor query. All this we can do in this time. But in the binary search tree, red black tree, what is the how to do the successor query? Like if we draw this tree, balanced tree, suppose we have a balanced binary search tree. Okay. Okay. Suppose we want to find the successor of this element. Now, who is the successor of this element? Any idea? Who is the next element after this? Or this may not be in S, but this is a successor query can be for any keys from the universe, not necessarily in S. But anyway, if it is this set, if this is our X, then who is the successor of this X?
So the top node.
Yeah, so this is the node. We have to just traverse at the top. I mean this node. So this is the successor. So we have to any case we have to find the we have to take this path. So if this is the height, if this is the maximum level, so this is the height. So that's why this query will take log n time. But here we are not assuming any thing for the fixed universe. We are not caring about whether these are coming from some fixed set, So we know the universe. That information we are not using here. This is just we are having some keys, a set. We are having some keys. Then we are forming this tree. Then we are doing this deletion, insertion, or successor query or predecessor query on this, without assuming this that we have some extra information about this. So now the question is, sorry. So now the question is how we can use this fact, how we can take help of that. I mean, we should use that our keys are coming from this universe. So any suggestion, any other data structure? Any other data structure? In fact, we want to do it in very faster way, like not just log n. We want to do it in log u time. So that we'll discuss today. Yeah. So that is the goal for today's class. We want to do it in this time. We want to do it in log u time. Okay. This is quite faster than log n, right? Log u. So that data structure was proposed by this Peter van der Newell's data structure. Peter van der Newell's in very old, but this is very cool data structure. We'll learn that. We'll basically use the lot of argumentation in here. So this is our goal. We want to do it in log of log u. So now the question is how one can get this. I mean, this time complexity, log of log u. How to get this time complexity? For which problem we can have this type of, which algorithm can give us this? Any idea? We have seen log n, we have seen l log n, but how to get log n? I mean, log u. Any idea how to get log? This is another bracket. When to get the log? Any problem you can think for that? We can have a code for which will get log u. Log u. What about binary search on the log u elements? If we do the binary search on log u element, this is our new m. So that will cost us log u. Anyway, but we want to have a recurrence for this. We want to have a recurrence which can give us the solution will be log u, and that recurrence is this one. So if we have this recurrence, tu is equal to t root u, so plus the constant, then this, if we put this just u to be log u, then it will give us the solution log u. So basically our goal is to achieve this recurrence. So that we'll see slowly how we can achieve this recurrence for our problem like successor query or insertion. So that is our goal for today's data structure. We want to achieve this. We want to have a data structure which can give us the successor query, this recurrence. Tu is equal to t root u plus constant. So for that we have few steps. So first step is, can you think for an array of this problem? We have given some set S, and we know the universe. Can you think for we have seen the array of S. Instead of array of S, so we have some set S which are some numbers, say 1, 9, something like that, 4, 6, and we know these numbers are coming from our U is say 16. So these numbers are keys are coming from 0 to 15. So this is a subset of, that is our universe. This is a subset of 0 to, so any keys, any values has to be between 0 to 15. Okay, so this information we have. This is called fixed universe. We know the universe. We know our U. Now, can you think for another array data structure, so that we can do the search and insert all this thing in a faster way?
I mean, we can just have something which marks whether the number is present. So we'll have this set of, u number of elements, and then all
Yeah,
those indices which are present can be marked with 1 and the others -1 or 0.
yeah, yeah. So that is the idea. So we can have an array of size u. So instead of array of size n, we can have an array of size u. Sorry, bigger array, which is starting from 0 to u minus 1. Which is starting from 0 to u minus 1, and this u is this u is the set of universe, which is just coming from so for here our u is 0 to 15. So 0 to 15. So we can, so suppose these are the elements. So how to insert? We'll put that, if the element is present, we'll put 1, otherwise we'll put 0. So 1 is present, so we'll put a 1 over here. Then 4 may be here. We'll put a 1 over here for 4. Then 6 is here. We'll put a 1 over here, and then we have 15 over here. Yeah, no, 9 is here, so 9 is here. We'll put a 1 over here. So that is just a simple bit vector. We have seen earlier this type of data structure. Very cool data structure, very powerful in the sense we just need 0, 1 to indicate that whether this keys is present or absent. Okay, so that is the representation of this. So we have here, so we just put a 0, 1. So we can have for this set, so 1 is present, so we put a 1 over here, and there is no 2's, no 0's, so we put 0's over here. 10, we have a 1 over here. 9, we have, so very just a 0, 1 representation, just one bit of information we need to have this. Okay, so for that, so how to do this insertion and deletion is very trivial in the sense just a constant time. We can have this, just we go to that field. Suppose we want to insert say 8. So what to do? We go here, we go this position, and we just have we just make it 0 to 1. So that is the insert operation. Similarly delete. So if you want to delete 9, we can go there and we can just make it 0 if it is 1. So now but how to do the successor query? Suppose we want to find the successor of say 1. Successor of 1 is 9. So we have to traverse this list from after 1 to find a after this one to find another one. So what is the worst case runtime for the successor query? Any idea?
Order of n, I mean order of size of u, I guess.
Yeah, order of u. Yeah, correct. So the successor will take order of u time, because in the worst case maybe we are looking for an element which is just for that we have to traverse the halfway to this list. So maybe u by 2 or u by 3, u by 4, u by 10. So in the worst case, because we are not doing anything on this, just a simple array, just a bit vector, presence or absence. So this will take the order of u in the worst case, because maybe we have to traverse this array. Okay, so that is not a, but this is the very starting point of this data structure which we will discuss. We will do lots of augmentation on this data structure. We take this data structure, the bit vector, then we will do some augmentation. So now this is an array of size u. Now we what is our goal? Our goal is to break it into root u. So how this is a one dimensional array. So how can think this array? How we can break this array into root u? Any idea? This is the array of size u. We want to break this array
Square
into
root decomposition.
Yeah, so we can think this as a, we can break this as a two-dimensional array instead of one-dimensional array. I mean just a matrix form. So this is of 16 size. So if we can have a 4, so this is first 4 bit. So root u is 4. For this example, we this up to this is first 1D array. So this is basically we are breaking into square root form. So this is next one, this is next one, like this. So this is our just square root of, I mean square root into square root will give us square root of u will give us u. So we have a total size u, we want to break it into matrix form, I mean square root of u. So because our goal is to bring that recurrence, tu is equal to t of root u. So for that we are doing all these things. So we'll just think this array is this one dimensional array as a 2D array. We know 2D array, if you are familiar with C language, we know the 2D array or widget. So that is the blocks or sub arrays, we can say. So basically we are breaking, this is first widget. I mean we represent starting is 0 0 because we will do it in binary, then that's why we are the 0 to u minus 1, that's why we have taken that. Anyway, so this is the first block or the first sub array or first widget. This is the next one, this is the 0th one, this is the next one, like this. So just we are thinking this one dimensional array into two dimensional array. So in general, if we have u, so how many blocks will be there, how many sub array will be there, root u sub array will be there. So root u widget will be there. So this is the 0th widget, the first 1th widget, 2th widget. This is for u is equal to 16, then root u is 4. So we have four of these sub arrays. Just think about 1D array, how to break it into 2D. Just first 4 is just first 1D, second like this. So this is W0, W1, W2, W3, like this. We are just splitting the universe into the sub array or widgets. Okay. So now this is the if we want to make it in 2D form. So this is the first subarray W0. This is the next subarray. This is the next. This is the next. Sorry, this is the next subarray. And now this is the, so in that subarray we have this root u elements are there. Root u, each of this size of each subarray is root u. So here u is 16. So it is 4. Okay. Now in that case, how to do these operations like in 2D form? Suppose 1. So what we do, we convert this every element in a binary form. So here u is 4, so 4 bits. So 1 is 0 0 0 1. So we break it into two part, high and low. I'll explain high and low. So this is high. So this will represent which subarray, and this will represent the position in that subarray. So for 1, this is 0, high of x is 0, this is our x, this is our x is 1, the first element, and this is the low is 1, low of x. So we go to W0 and we go to that 1 position. This is starting from 0, so we put a 1 because 1 is this one. Similarly for 9, so how to represent 9 in binary? So 9 is nothing but 1 0 0 1. So this is 9 in binary. Here u is 4. Sorry, here root u is 4, u is 16. So this is high of this. This will represent the subarray number or widget number. Sorry, and this will represent the position of that element in that particular subarray. So this is W3. We go to W3. And then this is, sorry, this is 8. This is not 9, right? This is 0.
So it is 9, sir, but it is the first 2 bits are 2, it's not the 3.
This is 1. Yeah, this one will be 1. Yeah, not this one. Yeah, 15 is this one. Okay. So for 9, Yeah, so this is, oh, sorry, this is 2. Sorry, sorry,
The
sorry.
high
Yeah,
is 2, sir.
yeah, high is 2, sir. Thank you. High is 2, not 3. So we go here, W2, and then this is 1. So we go to here. So I am confusing with 15. For 15, we had this is 0. So for 15, we are here. So remaining are all are zeros, basically. So the same thing, this is also bit vector. So just a presence or absence. Only thing, we are breaking this into, we are splitting our universe into widgets. Okay. So this is the represent. This is the general form of this. So if we have u, then we are making into W0 to W1 up to W root u minus 1, and then each of these having this many. This is the size of the corresponding subarray in that widget. So each are like this. This is the general form. Okay. So now this is also we have discussed. So we are breaking into every element, we are converting into binary. So and then we are breaking into equal part, half half. So this is this side is so this will be again square root of u size. Yeah, so no, we are breaking into binary, then the half part we are making into this way, high of x, and the remaining half, the last half, the least significant bits, we are making into low of x. So the high of x will represent the wizard sides, wizard number, the subarray number where you should go, and this will represent the position of that element in that particular subarray. That's all. Okay. So this is how we'll do the insertion and deletion. I mean how to locate the element in that splitting things. Okay. Okay. So now suppose we have this arrangement. This is our current set of dynamic set S where we have these numbers. Now we want to find the, so what is so we have seen the successor insertion and deletion is simple. We just need to convert it into binary, then we go to that particular widget and we insert that element in that corresponding position. Okay, so now we want to do the successor query. Suppose we want to do the successor of some element, suppose successor of 2. How to do successor of 2 in this setup? So come here. Okay, suppose we want to do successor of 2. So this is our, so what to do? We just convert to, this is x is 2 over here. We have to locate 2 where it is. So 2 is nothing but we have to break it into binary, 0 0, then 1 0. So this is our high of x, this is our low of x. So this is 0, so we must go to the W0. So 2 is in 0 to z, and this is our 2. So this is basically our 2. So we are looking for a 1 after this. We are looking for a 1 in this arrangement after this. So how to do that? So we first search 1 in this in this block or in this subarray after this. So after this position, we first look for a 1 in this block or in this subarray or in this widget. If not, then we'll go for the next widget. So next is the W1. We'll next look at the 1. We start from the beginning and we search for a 1. But there is no 1, there is nobody there in this subarray. Then we look at the next subarray, that is W2, and then we search for a 1 from the beginning. So we got a 1. So we return this. This is in 2, so we again convert this into binary, and this is position is 0 1, so we again convert into binary, so that will give us 9. So we return 9. So successor of 2 is 9. Is this okay? So this, how to do this successor. But here, what is the time? Time is again, what is the time complexity for our algorithm which we have just now discussed? Any idea how much time?
So order of U only, sir.
Order of U, because we are just, it may happen that we may have to traverse order of U uh, visit. So we're not gaining anything out of this. But we do something there. We can have some information. We can do some argumentation in this data structure in the sense that how to save some time over here. Can you suggest?
So if
How?
we could indicate if there are any elements in particular
Yeah,
widget.
yeah. Because when we are searching for successor of 2, we are just we are just traveling this widget where we know there is no where there is no ones. So somehow if you can put this information whether this subarray is totally empty or not, then it could save our time to traverse this subarray, because if we know for sure that there is nobody in this room, in this block, in this widget, then we should not traverse this. So that information that argumentation we are going to do. So basically we are going to have another bit of information for each of these subarrays to indicate that whether uh, whether this widget is empty or it is somebody is there in this block or this subarray. So that is the argumentation we are going to do. So yeah, so all are zeros over here. So we'll put this field to be 0. So and this field there is a 1. So this will handle in the times of at the time of insertion. Sorry. So how to handle this? How to insert this? So this is our new argumentation. So now our data structure, we are doing some. We'll do more about argumentation on this. This is the first argumentation we did. Not first, we break it into the subarray, then we did this. Okay, now how it will help us if we have this information? How it will help us? How to do the successor query of 2? Sorry. So how to do the successor query of 2? If you have to find the successor of 2.
Indicator array element and you see if it's empty. So you just keep checking successively till you find one which has some element in it, and then you search within that.
Yeah. So first, if we have to find the successor of some element, we first locate that element in which subarray it is, which widget it is. So for 2, we first look at the 1 after this position, where after locating that. So there is no 1 over here. So then that means we have to go for the another block, another subarray to search for a 1. Now then we go to here. We check for a non-empty subarray, next non-empty subarray, because there is no necessary to traverse this, because if we check this 0, that means we know that there is nobody here in this room, all are zeros. So this is a kind of empty subarray. So we will not traverse this, we will save the time just by checking this value. So this is 0 means there will be nobody in this block, in this widget. So then we will avoid that. Then we will find so basically we will again find a 1. This is also a successor. Just think of it. This is a successor of, after this block, after this position, this is a successor call again. We have to think that, because ultimately we are going to have a that recurrence. For that we need to have the successor call. Anyway, so we are basically finding the successor of, if we think this is a array also, we are finding the successor after this in this. So basically we are finding the next one after this. So next one is here. So that means this position is 2. So that means we know that there will be somebody in this block or in this widget, someone will be there. In that case, what we do? We just go to that particular block where we know that there is a 1, and we start from the beginning, because we don't know where it is the 1. We know there are 1s. We don't know where the 1 is. So we have to start from the beginning to search for a 1. So then it will take. So is it clear, the successor query for this data structure? How much time it will take?
Sir, in the non-empty column, we are putting binary digits only.
in a non-empty column we are putting 0, 1. Yes.
So at the time of deletion, we will have to traverse that whole widget, right?
No,
To
when,
update.
yeah, so I'll come to that. When we insert, suppose we insert say 6. Suppose we want to insert 6. How to insert 6? Suppose our x is 6. We want to insert 6 in this data structure. So new element insert. So what to do? We break it into, we convert into binary. What is 6 value? 6 is 0, 1, 1, 0, right? This is 6. Yeah, this is 4 plus 2. So this is high of x. This will represent our number. This is low of x, position of this 6 in that. So what is this value? This is 1 and this is 2. So where we will go? We'll go W 1, and if we think for a 2-dimensional array, then we go to 2 and we make it 1. So we go here. So this is this one. Yeah. So we make it this one, and then we have to check this field because we have inserted an element. We don't know whether this was 1 or 0. We don't know. In that case, we have to traverse all this, or we have to check that. So anyway, we just go to this non-empty. If this is any array, you can say. So what to do? We go to any of, this is again a 1-dimensional array. This is any of what? Any of high of this x. Any of high of x. This is 1. We'll put this one to this any, the non-empty array, to be 1. So this will make 1. Similarly for deletion. So if you want to delete this 1 again. So yeah, yeah, I got your point. So you're telling if you want to delete this, if there are more than one element in the more than one keys in the sub array, now if you delete this, then we cannot make it 0 because we are not sure that there are other elements, other keys residing in this widget. So in that case, we have to traverse this list.
Yes, sir. So why don't we store the count in that non-empty array, the count in the widget?
Yeah, we'll do that, not count. We'll do some more augmentation here to save that. Yeah, you are correct. So deletion is, for deletion we cannot just make it 0 because in that case we have to traverse this list to ensure that there is no one. So yeah, okay, we'll do that. Yeah, so that is one good idea to have one more augmentation here to have a count on this. So if we store this, in that case, if we store the count number of elements, so in that case we are storing the some integer here. So here only we are only storing the 0, 1. That is very 0, storing 0, 1 will save us less time than the storing the some integer numbers. Anyway, we'll do that. Okay. Any question? So how much time it will take for this successor or insert? Insert, we know we have to go there, and insert is constant time, right? We just need to go there and just make it one.
Sir, successor is 2 root u.
Yeah, successor again is order of root u because
अरे ऐक ना, तुम्हाला 3000 किती हा तू 3700 वर्ड दाखवले ना मला. आवाज नाही येते का?
let me unmute you again. Can you mute your mic if you are not speaking? Yeah, so yeah. Yeah, so successor is basically order of root u, but insert will take constant time, that is fine. So this is the successor, what we have discussed just now. What we are doing, we are just finding the, we are breaking into the binary, then we are finding the high of x, low of x, and then we are look for the successor of x within the subarray, within the widget. So our widget is w of high of x, right? In that widget, we are looking for a 1 after x. I mean after this low of x, because low of x is the position of this x in that particular widget. So if successor found, will return happy day. So that will cost us just root u, because so suppose successor of 2 we are finding. So we just scan this after this 2. So that will cost us square root of u, because this each size of this block is square root of u. So if not, then we are finding the smallest I after this high of x, because we don't know where is this x is. So after this high of x, so this is our arrangement. So we have some 2D blocks. Each of these block size is square root of u. And how many blocks are there? Square root of u blocks are there. And we have another field which is of size square root of u. This is also square root of u, to indicate whether this block is empty or not. So we have some x over here. This is the w of high of x, say high of x, and this is our low of x position in there. So we first look at the one in this. So that will be this step. So first step. So if you get a 1, if you get a successor, we return that. Otherwise, so this is again the that array, summary array or non-empty array, whatever you want to say. So S array, summary array, something, or non-empty array, whatever. So this is our this position is sum of high of x, whatever the high of x value is. So we have to look for a 1 after this. Basically, we need to look for a I after high of x which is having 1. So that is also another successor call we can have. We can think of it. Okay. So that is the smallest one, because we are finding the next one, the immediate one, successor is. Okay. Now suppose this is the I. We got a I where this is non-empty, this is 1. So we know that in this wi there will be a 1, but we don't know where is this 1 is. So you have to find the smallest element in here. Say suppose this is j, where there is 1 is. So smallest element means we start from the beginning 0 to, we find the next one. So that is our, and we return that. So we return the smallest element there, where is the 1 is. So this is the idea. So we have a so basically here also this is successor call. Anyway, so this is the runtime of this code. Is this? Yeah. So this will cost us order of u, because we don't know. We may have to traverse the whole subarray. So that is order of root u. And to find this next smallest element, next I, where is the 1 is after high of x in that non-empty array or summary array. So that will also, because size of that is again root u. So we may have to go for the order of that size of the array, which is root u. So that will cost us root u. And again this find the, we know there is a 1 in the wi, we have to find the first one. So that first one may be after traveling a size of the order of the size of that particular subarray. So anyway, so this is cost us order of u algorithm. Order of square root of u, because if you sum it up, it is 3 square root of u. So it is a runtime is order of root u. Any question?
Sir, can you explain high of x and low of x once again?
Yeah, high of x is basically so we are, I'll explain here. So suppose we are finding the successor of say 6. So for that, what we do, we represent 6 in binary. So 0, 1, 1, 0. Basically, you want to find the position of 6 here in this 2D arrangement. Okay. So for that, this first half, so we break it into two halves, equal halves. So this is least significant half, least significant bits, this is most significant bits. So this least significant bits is our high of x, and the most significant bits is our low of x. Now low of x. So in the binary form, so what is this high of x represent? High of x is representing where the 6 will be in the which subarray or which widget. So 6 will be, so this is, if we just think this as a one dimensional array, this is 0, 1, 2, 3, 4, 5, 6. So 6 has to be here. So that's why it is just a 1. So W1 which will contain 6. And then this will represent low of x. Low of x is 2. So 6 is nothing but here. Okay. So that is the idea. I mean, we need to find the position of that x in this 2D arrangement, so that we can yeah. Any question?
Sir, it is valid for when the u is 16, but when u is in general some n
Yeah.
square.
So yeah. So for so that is not possible. We have to assume that we are making this database for u is 2 to the power some power. Okay. Because after that we will break it into, because recursive call we will do. So there we have to again break it into this square root of u again has to be break it into square roots of. So we'll come to that. Yeah, you are correct. So here we have an assumption that this should be. Okay. So now what is our goal? Our goal is to get this sorry, where is my goal? Our goal is to get this recurrence. So tu is equal to t of root u plus some constant. If we can have this recurrence or successor call, then we can say this will give us log u. So we want to have this recurrence. So for that we need to think for a recursion call because unless we think for a recursion call, then we cannot write this type of recurrence. Okay. Now think for this successor, finding this successor in that particular widget. This is also a recursion call, recursive successor call, because we have to. So what we are doing, we are just to recap. So we have this subarrays or widget. So sorry. So this is, and we have this summary array. Okay. Now we are finding the position of x. So if x is somewhere here, so then suppose this is our x position. So this is our w of high of h of x, and this is our low of x. So what we are doing? We are first in the first step. What we are doing? We are first looking for a successor after this position in this particular subarray. So for that, this is also a successor call. Again, if we call it, then again it will break it into 4 part. I mean, sorry, size of square root of size of that. So that way. So just think for a recursive call. So this is a recursive successor call. So we have a successor call over here. We are just trying to find the successor of this element in this particular widget. Okay. Now you found, okay, happy. Otherwise, we have another successor search. We have another. So this is our summary bit or non-empty bit, whatever you feel. This position is sum of high of x. So what we are doing, we are basically finding a 1 after this. So that is also successor call in this particular array. So this array size is square root of u. So that is, again, that will be a recursive call. Again, that will break it into square root of size of that, something like that. So we got a I over here, say successor call will give us a I. If there is no, then we have to say no successor here. So we got a I, so you have to go for wi, then we have to search for a successor of what? Then we have to suppose wi. I is this field where we know there is a 1, but we don't know where is the 1 is. So we have to find the minimum index where is 1 is. So what to do? This is also successor call. Successor of whom? This is also successor call. We are just finding a successor of whom? Can you tell me? So we know in this field there is a 1. In this subarray there is a 1, at least 1, because this non-empty bit is 1. So we have to search that first index. This is successor of what? Any idea? This start from 0, index start from 0, 1 like this. We cannot say successor of 0. In that case, if it is 1 over here, we'll miss that. So it is successor of some minus term, maybe minus 1 or something. So we denote the successor of minus infinity like that. So any minus of 1 because we cannot say this is a successor of 0. In that case, we'll miss this 1. So it is a successor of any minus term. So basically we represent that by a 1. So this we have already discussed. This is, we are taking the summary widget or non-empty widget. So this is the general form. Okay, so this is the way we represent it in the 2D way. So we know this is the two-dimensional way we represent, and this is our summary bit or the non-empty bit. Yeah, so just we want to write this in terms of this successor call. So basically we are finding this is sorry. Yeah, so this is the pseudo code for that. This is 1, 2, 3, something like that. Okay, we want to get this time complexity of this. Basically, we want to get that recurrence. Okay, now just think we have a data structure, that arrangement where we did some 2D arrangement with a special summary bit there, summary subarrays, summary arrays where we are putting the information about this emptiness of this widget. Okay, so now we are first calling, we just find this. So this is our we have drawn this picture so many times, and we have these summary bits. Okay, now we find the position of this x over here. So that is in that w of high of x. This is w of high of x. This may not be the first one anyway. So now we are finding the successor. This is the low of x. We are finding the successor of this in this widget. So this is also a successor call, but here this is a subarray. This is a whole array. This is a subarray after this low of x. So if we get it, then we return it. So if we don't get it, then we have to find a non-empty bit after this high of x. So that is in summary call, successor call over here. So that is will give us some I where there is a 1. So suppose this is the I where this is 1. So this is also successor call after the high of x. So now we have to find the we know there is a 1 in this wi. So we have to find this successor of minus something, say minus infinity. So if that is I, then we return this in a integer form. We return this. So this is the successor. So how many calls? We have 3 calls. So we have 3 calls. We have 3 calls over here. So this is this will take square t of root u, t of root u, t of root u. So what is the time complexity? Time complexity will be 3t of root u plus theta of 1. But that will not give us log u. So we don't need this 3. we want only one successor call. So that is the some more documentation we are going to do. So how to do that? Any idea how to save some call from here? So we need to reduce the successor call. We need to reduce this call. So if we have one call, then we achieve this. So sorry, this will be routine. This will be U. So basically we want to have just only one call. So the question is how we can have a one call. So can you just suggest how we can have one call? So, sorry, let me just get the picture, then I'll just, yeah. So can you just suggest how to have one call? So look at this. So how to avoid these calls? So is this call is required? Can you do some more argumentation to avoid this call? Any suggestions? So this is our widget. Now these are our summary bits. Okay. Now here, suppose our X is here. Now we are having a call over here. So can we avoid this call in order to have some more argumentation in this data structure? Can we avoid? Any idea? Can you have some more information over here, more argumentation in this data structure? Some quick suggestion. So this is summary bit. Now what about if you store the maximum? If you store the maximum index here for every field, because we don't know where is the X is. If you store the maximum index, where is the one max? This is max. That means if you store the maximum, where is the last one? Then if we just check the maximum, and if the low of X, if the low of X is greater than maximum, then we know there will be nobody ones over here. So there is no question of do this call. So if the maximum is greater than low of X, then we are sure that there will be a one over here. Then there is we can do this successor call, and we got that J. We will be getting that J. So just a one call. So just we have a max field over here. Max field to indicate the maximum index where is the last one is, in order to avoid surety. Like if we just check we found low of X, we have to get the successor of after this there is a one or not. So if we check the maximum, if the maximum is here, or it could be this also, then there is no question of looking at one in this subarray. So we just ignore that. But if we know that maximum will be somewhere here, after this we'll do the call. We'll go for the successor call, and we got the one. We save the time. Okay. Now,
Sir, maintaining that maximum will not
Yeah.
it hamper the insert deletion?
yeah, maintaining the maximum where we'll put this, then we'll check this max value, and we know the index. Then if that index is less than, then only we'll just update that way. Okay. Anyway, I'll come to that inside and delete. But let's just okay. So in that case, so if we do this augmentation, then what is the successor? So what is the time complexity of this code? Then if so how many calls? So if there is a one, then only one call, but we don't know whether we'll get this one in here or not. If we don't get it one here, then we have to have this call. So that will be one call, and then we have another call, two calls. So now we have to think to save one more call. How to save one more call? How to save particularly this call, last call? Last call is required. Can you do some more argumentation over here? Any idea? Can you store some value over here so that we can avoid the last call? What about minimum? We stored the minimum. Where is this? We stored, this is our, this say we have returned this I. We know there will be one over here. Now if we store the minimum over here, come to something like that. If we store the minimum, then we don't need this call. We can just take this minimum from this field and we just have a one call basically. In the worst case, we just have a one. Is this clear? So we are doing so many argumentation in this data structure. We are storing the maximum to ensure that if there is a one after of x, we'll just get. If not, then we have then we have a two calls over here, because first call will give us the non-empty subarray, and in that non-empty subarray we have to get another call to get the first one, so that also we can avoid if we store the minimum, this minimum index, where is the one is. So this max minimum will, so this will ultimately give us order of just a one call. Is this okay in the worst case? Yeah, you are correct. If we have to insert it, then we have to just so yeah, so this is the one call, and so this already we have discussed. So this already we have discussed. So we are just putting the minimum, max field and min field. Yeah. So when we are inserting, we have to be careful there. When we are inserting, we have to check that low of x. When we insert a x, we have to check that particular low of x. If low, we check the max field over here. So max of high of x, and then if that is if the max field is less than low of x, then we need to put this that low of x. Similarly, for min field, if the min field is the existing min field is greater than, then we have to change that. So that we can easily.
The problem will be mainly while deletion. Suppose that we are deleting the max, and then it has to check the next maximum. So it makes the whole widget to traverse.
Yeah. So can you think for a deletion? Deletion, I since the time is not there, I'm not discussing now. So the deletion also little tricky over here. How to delete it? So what is your suggestion? If we delete it, then
so if I delete the maximum, then it has to traverse the whole widget to fix the next maximum. So
why? So suppose we have this. Is the deletion is not same as insertion? Let me check. So we have this. Sorry. So we have few fields over here. Summary, max, min. Okay. Now, particular this one. So suppose this is summary bit, this is max, this is min. Suppose we are deleting some element over here. So if we go to that particular x, low of x, high of x, and then if we yeah, we can check the max min. So no, if we delete it, then if we check the max, if this this low of x, if the low of x is less than that max of whatever value over here, high of x, then we will not do anything there, because there is somebody wants over here after this, so we will not do anything over there, right? Because we are deleting this guy. This was one, we are deleting this guy. So if the max is something which is after that somebody is there, someone is there, so that is our maximum field. So if we check just this one, if the low of x, if this is less than this, then we don't do anything. And for the minimum also same thing. So if the low of x is greater than minimum of this high of x, then we don't do anything. Is it not?
Sir, I am saying to delete the max. I am not delete the which is max. The
Oh, if we are telling that if it is equal, if it
yes,
is,
we have to
yeah,
fix the next max.
yeah. So if it is, yeah, so that make so deletion. Yeah, you are telling if that is itself is a maximum, right? That is you are telling.
Yes, sir.
Then how to handle that? If that itself is a maximum or even minimum, because we are doing storing both of
Yes,
maximum
sir.
and minimum, then how to handle that? Then your suggest no. I think you can handle it. I mean, you can have some more argumentation over. Anyway, think about it. Okay, I got your point. You are telling if it is not maxim mean, then we are safe. You are telling if it is if it is maximum. If you are deleting an element which is the maximum one.
Yes, sir. Specifically, if we have only two elements, one is sitting at the start and another at the end, and we have to if we delete the any of one, then we have to traverse to whole the widget for
No,
finding.
no. Can you do something more? Some more argumentation to avoid that. Think about it. You can do it. Okay. What about the second max if we store something like that? If we do the, I'm not sure about that, but you can just think for some more argumentation. Okay, so that is the data structure, which is we did lot of argumentation on our just on the array. So this is called Van MDMOS data structure. This is very cool data structure. Okay, so I'm stopping now today.